afternoon. The first one here is the In-Space Power Systems panel. And I think we have some great participants in both of these panels. You know, as space systems get larger and we endeavor to return to the moon and onto Mars, its power systems become growing importance as part of the in-space equation. In fact, I would call it one of the real keys to sustainable operations. How will we generate, store, and distribute this power in the harsh environment of space? Temperature, space radiation, and system compatibility are some of the drivers for the new systems under development. So please join us for an electrifying conversation on in-space power, the new directions being developed. Our panelists are, I'll introduce the panelists now. There's four. Karin Bozak is an electric power systems project manager at NASA Glenn with over 10 years experience in the field. She has a bachelor's degree in electrical engineering from the University of Akron and a master's degree in space systems engineering from Stevens Institute. Darvin Remington is the chief engineer within Moog's space sector and has over 30 years of experience at Moog. Darvin is currently Moog's principal investigator into in-space high-efficiency power conversion technologies that are appropriate for human landing systems. Joe Troutman is a business development manager in medical and space for EnerSys. He has over 30 years of experience in the space power system area and also supports the implantable medical device industry. Joe is a recognized expert in lithium-ion battery technologies and serves on several committees and boards of directors. And then June Zakrajsek has over 20 years experience in aerospace systems research, development, and project management. She's currently the program planning and assessment manager for NASA's radioisotope power systems program. June owns a master's in biomedical engineering from Case Western and a master's and bachelor's from mechanical engineering. So what we'll do now is invite each of the panelists to provide some open remarks. And they're I remind each of you to try to keep it within 5 minutes or so. Then we have a couple topics that we'd like to have discussed as a panel and open it up for questions. And with that, I'll turn it over to Karin.
Thank you, Jim. It's a real pleasure to be here virtually with everybody this afternoon and share some thoughts on power systems, both in space and the surface, to enable sustainable exploration. If we could go ahead and show, I just have one chart for you, but we can go ahead and look at that now. And I'll start talking it because I only have 5 minutes. But really exciting is what I know our administrator Bridenstine shared yesterday, that we want to land the first woman and the next man on the moon by 2024. But this chart, I think, depicts sort of the next chapter in our exploration goals of how ARTEMIS will prepare us for Mars. And some of you may have seen this, to others this may be new, but I think a key piece of this is sustainability, both in our lunar orbit staging capability as well as on the lunar surface. I'm not going to read everything on this chart, but just point out a couple of things. As we sort of look onward to Mars, you see a lot more assets on the lunar surface, sort of scattered around and not labeled, a lot of smaller landers that enable opportunities for science and cargo payloads to demonstrate and prove out technologies and capabilities that we will eventually need for Mars, as well as a foundational surface habitat and habitable mobility platform to enable more crew to land, live, and explore on the surface. As you look at sort of the arch in this picture, you see the gateway, but this is not your sort of 2024 gateway with minimal capability. As you can sort of see over time, there's additional elements or modules added, included the international habitat, as well as I think towards the right-hand side, they talk about expanded habitat capability at the gateway as well. And this would enable us to really do a dress rehearsal or Mars analog mission, if you will, in and around the moon to prepare us for Mars. And so I have just a handful of power technologies I'd like to highlight. I know the other panelists have some as well, so my list is by no means a comprehensive list. But the first is the Advanced Modular Power Systems, or AMPS project at NASA. There's two sort of key areas here that will enable us to explore from Moon to Mars. And the first is that we're taking the distribution and conversion elements of your power system and breaking them down into the smallest levels or functions that we sort of call our building blocks, so that when you integrate those together, you can achieve sparing of the power system components at a much smaller level than what we see today on the International Space Station, where they have orbital replacement units, commonly referred to ORUs, that are the spares. In this case, we've got a smaller circuit card that could be spared in the event of a failure. And so obviously on ISS, we're fortunate we have lots of opportunities to perform logistics and have resupply missions. As we look out to Mars, if you have a component fail, it's not as easy to get a logistics resupply out there. So that will certainly improve the maintainability and logistics footprint of future space power systems. Another area within AMPS is our autonomous power control work, and this has the goal of enabling the power system to operate safely without human intervention. So in the case of the Gateway, especially as it expands to the additional habitats, there is still, I believe, only about 1 month out of a calendar year that Gateway would have crew on board. And so for those other 11 months, to make sure that the power system can sort of detect faults and safely recover from those is very important. Also on trips out to Mars or in the vicinity of Mars, there are significant communication latencies. And so sort of allowing the power system to operate without that human in the loop is a very important technology as well. I will highlight a couple of technologies that are currently in development under STMD, Space Technology Mission Directorate as well. The first is regenerative fuel cells. And those, as we look at the lunar surface, not just at the South Pole, but particularly some payloads we may want to send closer to the equator. The lunar night there could be equivalent of up to 14 Earth days. And so we want to make sure that if we're going to send something there, that it doesn't just operate through the day, that we can really get our money's worth and operate it through, multiple lunar day-night cycles. And so a regenerative fuel cell sort of has an advantage over maybe a traditional or rechargeable battery when you start looking at tens of hours or days of energy storage needed on the lunar surface. Another important technology is a vertical solar array technology STMD has started investing in, and in particular at the South Pole, where some research papers refer to specific points on the South Pole that are peaks of eternal light or nearly continuous light. And so if you're able to raise a vertical solar array and just point it along the horizon to track the sun, that's a very reliable power source there. Another important power source that has been in development for a while, I don't know if you're familiar with kilopower, but there was a ground demonstration, very successful back in 2018. Definitely search for it if you haven't heard about it, but I know that they're looking at sort of taking that concept, nuclear fission, and looking at technology demonstration mission options so that we prove it out not only here on Earth, but take it to the lunar surface as well. And that's an important technology. I didn't talk too much about the others, but this is one certainly with nuclear fission power that if you could prove it out on the moon, it translates exactly to what we need for Mars surface power systems as well, where you look at the Mars surface and with some of the recent dust storms they've had, it's hard to size a solar array. It becomes too large or heavy for the types of power levels we need for a human mission. And so the nuclear fission is certainly extensible, not just from the moon, but also to Mars as well. So thank you, and feel free to ask questions on these if you have any.
All right, thanks, Karin. We'll open up for questions a little bit later, but there certainly is a lot to try to fit in that's going on right now that you have to fit in 5 minutes. So you did great. Thank you. Darvin, do you want to go next?
Here I am. Yes, this is Darvin Remington. What I'm going to discuss here is, do you have the slides up? Are they viewable to the folks on this?
Yes, Darvin, the slides are visible, and we're seeing your first slide, which is the Space Power Systems panel session.
Okay, all right. So you move on to the next slide, which is titled Moog Arc Voltage Conversion Systems. And what I'm going to do here is provide a brief explanation of why Moog is investing in this technology and what we've accomplished. So to start off with, Moog has recognized the need for high efficiency power conversion systems for in-space applications. And Moog has been investing in that for probably 3 or 4 years now, culminating most recently in a demonstration at NASA Glenn Research Center of this device that we call an arc voltage converter. It goes by a couple of different names, so I apologize if we change the name a bit. Officially, it's called the Moog arc voltage conversion system. And so we demonstrated this technology in the lab at NASA Glenn Research Center. You should be seeing a picture, 3 pictures on the right-hand side of this slide. The larger top picture is actually a picture of the test setup at GRC. You can see the thermal vac chamber in the back of the room where the Hall effect thruster is being fired, being powered by 5 kilowatt arc at 500 volts DC. And then the bottom left-hand image on that slide is the actual piece of Moog hardware that was built and tested and demonstrated. And then the bottom right-hand picture is an image or a picture of the Hall effect thruster actually during firing. So that's where we've gotten to, and we continue to invest in this technology. Current activities include exploring gallium nitride FETs for their their radiation robustness in space, which is required, along with gallium nitride drivers, clocks, and also researching FPGAs. Fortunately, FPGAs are pretty well known, and there's many to select for this type of technology. I think that's pretty much it on this slide. The efficiencies that we obtain are about 97%. And really what we're up to next is actually coming up with a space-rated version of this technology. If you move on to the 3rd slide, the future of ARC. Based on RFIs that we've received and research done what NASA is doing on AMPS, we've come up with a modular technology that, with a modular technology because different applications have different input and output voltage requirements as well as power requirements. The concept that we've come up with basically employs modules that can be mixed and matched for various input voltages and scaled up for, and also mixed and matched for various voltage outputs. And the actual output power can be scaled. So if you look in the diagram that's labeled modular design architecture, the very top image shows a blue control card that contains the FPGA, provides the control of the power supply, power conversion system, as well as communications to the main, if it's a vehicle or main system. The pink modules shown there is actually the technology that was demonstrated at NASA Glenn, basically taking the input voltage, turning it into an AC waveform, transforming it, and then rectifying it back into 400 volts, which goes through the green blocks and produces 250 volts each. Those slices in this case are stacked to produce the total of 500 volts required by the thruster that was demonstrated. Similarly, down on the bottom, concept number 2, we're using the same control card for a different input voltage and output voltage requirement. In this case, it's showing 120 volts input with a 28 volt DC output. We can have multiple versions or quantities of these modules to scale the output. Currently, each module is 2 kilowatts. And that technology, or that actually is currently in our prototype development. I was currently working on that green module, concept number 2. Let's see. So the other keys to the flexibility of the modular systems are that you design a single module once, thereby reducing the NRE across multiple applications. So for example, the control card ideally will be the exact same control card in all of the systems that Moog supplies. It features a reprogrammable FPGA so they can be customized with regard to what the communication protocol is, as well as the type of information that needs to be transmitted to the vehicle. I think that's pretty much it. I think I emphasized the scalability and the programmability of the system. And then if we move on to the last slide, I'll let you go ahead and read the pictures. I think everybody that's viewing this right now probably is well aware of where power conversion is required in space applications. And so there's some pictures of the applications that we are targeting. Moog will continue to invest our IRAD dollars into this technology, basically spacifying the electronics, and continue to search for a real application. And as I mentioned before, we have received RFIs from various customers, and we are targeting that information as the baseline for our specification. Thank you very much.
Thanks, Darvin. Yeah, I will definitely agree that modular systems is a real key to developing a sustainable architecture for ARTEMIS and that everybody can interface with. So thanks so much. Joe, why don't you take it next?
Sure. Hey, pleasure to be here today, and thanks for having me on the panel. I work for EnerSys Corporation. We're the largest industrial battery company in the world, and I'm part of the aerospace and defense group there, working on lithium-ion batteries, both primary and rechargeable secondary batteries for space and launch vehicle applications. And I'm going to talk about the battery industry today. Overall, the battery market is an evolving market today. It seems to be ever changing. Cost is king on most of the programs these days, but cost is king, but you still need to perform. So if you can just go to slide 1. This is a chart, a table here showing some results that came out of a NASA JPL decadal battery study that we just completed. Working with JPL led the study, and there was both battery and cell manufacturers part of the team, in addition to users and government labs. So the top few lines talk about NASA JPL missions looking over the next decade and what the battery needs are. And the battery needs really are expanding upon what is currently state of art today, both in primary and rechargeable batteries. On the rechargeable side, you can see for most of the future JPL missions, at least, we're looking at a battery energy density of greater than 250 watt hours per kilogram, which is beyond the state of the art today. If you take a look at that at the individual cell level, you need to be greater than 325 watt hours per kilogram. Most commercial and even domestically made lithium-ion batteries here in the US and across the world, the highest, say, let's take an 18650 format cell, for example. The highest energy density today is 268 watt hours per kilogram. So it's close, but not quite there. The one item that needs to be considered in all this, it's not just all about energy density, but it's also about DOD, how much energy are you going to pull out every cycle, and then how many cycles do you need over the lifetime of each program. So those three things intertwine. Nothing is free. So when we start to increase the energy density, we usually take a hit in cycle life, or be limited by the amount of DOD energy we can pull out of the cell. Another parameter that's been really identified as a key feature in these cells is the operating temperature range. If you look at the surface landers and rovers, the batteries needed for that need to operate anywhere between -60°C to +60°C. And depending on if we're going to the inner or outer planets, we might need to operate up to 465 degrees C. So really pushing the technology here. During the study, we looked at various chemistries. We looked at the standard lithium ion using NCA technology, silicon anode, which gives you a higher energy density, NMC, nickel-rich cathodes. We even looked at solid state using both liquid and solid electrolytes. And there's great technology out there. The solid states, showing great energy density, but they're having issues with cycle life to meet some of these missions. The same is true of silicon anode. It's a great chemistry to increase your energy density, but we're seeing a decrease in usable cycle life. Looking at the cycle life and column on this chart, you can see most of the missions for NASA at least are not too many cycles. Up to 1,000 cycles is very doable in a lot of chemistries. And then you have the long orbital or the flyby missions, long duration missions that are up to 60,000 cycles, which is a challenge for some of the newer chemistries. Looking at the commercial and the military, the secure space side, the bottom few lines on the chart, most of these are in LEO missions or GEO or MEO orbits. The cycle life is typically around 30,000. That's a 5-year LEO mission, just beyond a little 5-year LEO mission. They're pushing the DoD's usable energy out of the battery more, where they like to go, typically a LEO mission is around 20% DoD. They want to push it up to 40 and even up to 60% DoD with the higher energy density cells. Really trying to get the mass down, trying to get more of an enabling technology out of the battery system. And again, temperature is not a big driver for most of the military operations, typical 0 to 30 degrees C. So we go to the next chart, please. So this chart is a chart I've taken out of the SMC Space Force Technology Roadmap. And this highlights 6 major issues they see going forward in the battery area for secure space missions. And you can see the bottom box there, there's satellite computer issues, worried about cyber attacks from China and other rogue nations. Want to do in-orbit servicing, satellite hibernation mode, increased energy density in orbit, running at a higher DoD, dead bus failure, dead bus tolerance, and then again focusing on a reduced volume and mass. To get all those features, really, the Space Force is now looking at higher energy density, again keeping that long cycle life. They like to have a 0-volt tolerant chemistry, which means the battery could be discharged all the way down to 0 volt and recharged without any performance degradation. That is not a typical feature of commercial lithium-ion cells these days, but there are several companies that are offering a 0-volt chemistry in lithium-ion batteries. So this is all part of the space resiliency and getting a more secure spacecraft, either constellation or individual satellite. Most companies today are, again, to reinforce the scalable and modular approach to get more efficient, decrease the cost, and on the military side, also secure supply and domestically sourced materials is extremely important these days. Right now, in 2019, the U.S. was more than 50% import reliant for supplies of cobalt, 25% more reliant for supplies of lithium, and more than 57% import reliant for supplies of nickel. And they're all things we need to make our batteries, our lithium-ion batteries, for secure space. So back in December of 2017, there was an executive order that came out from the president to develop a federal strategy to ensure secure supply of materials here in the U.S. There's only one supply manufacturer in Nevada for lithium. So this executive order is going to look at how to get those resources more available in an affordable way. Having a secure supply of materials is critical to our strategic and military presence in space. We'll get into a warfighter domain, so resiliency is key. Additionally, the Department of Energy just put out an RFI on June 29th to industry in the U.S. Looking for renewable energies in support of critical battery material supply chain. So it is an issue, and we're U.S. is addressing it, which is good. So also, batteries, they're going for the future, are both needed in high energy, again, at increased energy density, but we also need high rate, high power cells. For example, thrust vector control, which is, Moog is one of the leaders in the industry on, needs extreme hundreds of amps, milliseconds power, but also we need to keep the volume and the mass of those battery systems down. So, next generation technology, batteries are extremely needed. Also, safety is a big push these days. Getting a safer battery cell, and also a safer battery design. At EnerSys, we're working with companies like ADA Technologies and their cell isolation material to prohibit propagation of a thermal runaway situation on a battery. That's part of SMC's Space Force also. The goal is to mitigate any risk with thermal runaways and batteries. So there's a lot going on.
Okay.
Battery development, and thank you.
Yeah, thanks much, Joe. A huge amount, and what I'll say is improving battery energy density and cycle life is really transformative to technologies and what we can do in space and on Earth. So June, we'll let you wrap up this part of the session.
June, you need to
are you
unmute
on?
yourself.
Hello, can you hear me?
All
Yeah,
set. Great. Thank you.
Okay, all right, sounds good, thank you. So good afternoon. I appreciate the opportunity to talk to you and share how innovations in nuclear power have an extended and will enable our explorations in space. You can go to the next slide, please. So specifically, I'm going to talk to you first about radioisotope power systems, or RPS, and how they've allowed us to visit the harshest, darkest, coldest locations in our solar systems. RPS takes the decay of the natural decay of plutonium-238 and produces continuous electricity that we can run our spacecrafts off of and our instruments. So humans by nature were explorers, and RPS is allowing us to explore these kinds of extreme environments. We've been doing that safely for 60 years. I think we heard that some yesterday in the conference. And from our standpoint in the program, we think that there are 4 themes that we can summarize what we do around. And that is the people, the power, the progress, and the production. So we, in the RPS program, we support NASA's Science Mission Directorate's Planetary Science Division. And we do that by staffing our program with a passionate and talented team. We have a cross-organizational team. We also have a cross-agency team. We have a very strong partnership with the Department of Energy. And that allows us to not only develop new systems, but also to deploy systems. We also have a very distributed leadership team. We have members on our leadership team that are not only from NASA Glenn Research Center, but also from NASA's Jet Propulsion Lab, as well as Johns Hopkins University Applied Physics Lab. And also we have Department of Energy directly on our leadership team. It's those people that allow us to develop the different power systems we have. You can see there the current power system that we have in the RPS fleet, and that is the multi-mission radioisotope thermoelectric generator, or I'll call the MMRTG. That's the one that's going to power Perseverance rover that's going to launch at the end of the month. And it produces about 110 watts of power. And so I kind of think about that, right? We have these rovers that are exploring Mars that are about the size of a car, and they're running on 110 watts of power generation. It's really a testament to the people again, to the engineers and scientists that can make those kinds of missions work. And that allows us to progress, allows us to understand better what kind of science is all around us in our solar system. And we also, we are allowed to look at that science differently because we can use nuclear power. And it's very unique. It allows us to go to the extremes. NASA Voyager mission is at the extremes, at the outer limits of our sun's sphere of influence, and probably will go beyond. And it brings back science that we would not have access to if it wasn't for nuclear power. And we're also making progress in the different types of systems. I'll talk about the RPS systems a little later, but I'm going to go back to a little bit that Karin was saying. We also are working with the Department of Energy to build systems that produce larger amounts of power, kilowatts of power. And that is being worked under the NASA Space Science Technology Mission Directorate. But since there's a lot of collaboration that needs to go on because nuclear can take advantage of the collaboration with Department of Energy as well within the different systems that we want to deploy within NASA. And so production, as we look forward to the different missions that we have to support within planetary, what we need to do is we need to assure the availability of the heat source material. And so working with the Department of Energy, we have reestablished the domestic capability to produce plutonium-238 in the United States. That's a capability we lost over 30 years ago. And now that we have that capability, some of the very first produced plutonium-238 is actually going to be in the heat sources that are going to power Perseverance rover. And so now what Department of Energy is doing is scaling up so that they can meet what NASA's forecasted needs are for the science. If you could go to the next slide, please. So what you see here is you see the fission systems. I talked about these larger power systems that we're going to need. And it's kind of like an integrated story. We're going to first start, as Karin said, with a demonstration of nuclear fission power on the lunar surface. And that's going to be designed such that it can support both Moon and Mars applications. The test objectives will align with both applications and will anticipate any kind of mission needs. After that initial demonstration, it's anticipated that we could either use multiple systems like that or actually include larger systems. And those systems then would allow us to go further and provide reliable sustained power on Mars so that we can open up safe human exploration of Mars. And then lastly, if you look at that progression, what we can learn and we can inform the designs might allow us to even provide higher power reactors that we could use for nuclear electric propulsion systems that could also enable the Mars transportation architecture and potentially future deep space exploration missions. You could go to the next chart, please. Thank you. So it's an exciting time to be in the RPS program. As I said, the Mars 2020 Perseverance rover is scheduled to launch on July 30th. It's going to look for scientifically interesting samples along Mars' surface, and it's going to put them in small packages that in the future, there should be a potential mission that can bring back those packages to Earth so we can study them. Also, in 2026, you'll see there in the middle a picture of Dragonfly. It will be the 4th New Frontiers mission. It's going to send a rotorcraft to Saturn's exotic moon Titan. So it's kind of exciting to me. This is a rotorcraft that's also pretty large, just like Perseverance and Curiosity. And it's going to fly across Titan's surface. And when we do that, Dragonfly will end up traveling further on Titan's surface than any other spacecraft NASA has sent, any other planetary body. And then what we're using to power that, we're using, again, the MMRTG. Again, 110 watts of power and heat. So in addition, on the outside of that, the slide that you're looking at, you'll see the new innovation that we're putting into technologies within RPS. We're looking at a dynamic radioisotope power system. It can provide 4 times more efficient a system than any other RPS developed to date. We could demonstrate that in the deep craters on the moon.
Okay.
Looks like June dropped out, Jim.
We may have lost June. What we'll do then is go on to our topics. I think she was getting close to the end anyway, so hopefully she'll join us very quickly. But what we'd like to do is spend maybe the next little under 15 minutes or so to talk a topic or two, across the panel, and then open up for at least the last 10 minutes for questions. And so the first topic that I'd like to pose to the panel is to discuss the biggest challenge you see in advancing the in-space power systems field, including any international competition considerations. And I think I'd like to hear from the industry partners first. So Darvin, if you'd want to take the first cut.
Yes, certainly. So from the viewpoint of power conversion and what we're working on to achieve power conversion in space, there's actually two aspects of electronic component availability that are a challenge for this technology. The first, obviously, is the radiation challenge for long durations. So there's work that needs to be done there, and testing and analysis that needs to be done there, and demonstration, of course. And then the second part of that EEE parts availability actually plagues many of the electronics that Moog launches into space, and that is basically the current marketplace for EEE parts is focused on the industrial and commercial markets. They no longer serve in a high regard the military, aerospace, launch type markets. So the industry, our industry is going to need to be able to determine how to use commercial off-the-shelf parts, in these type of applications. That's what I got.
All right, thank you. Joe, do you want to add to that?
Yeah, sure. As I said in my remarks earlier, I think one of the big challenges for us is as we look to evolve the batteries into these higher energy density solutions for our mission needs. It really is the domestic source material, things we can do here in the U.S. that we don't have to rely on foreign countries for. The U.S. spent $140 million setting up a domestic battery product line. We have one company that produces the domestically sourced material here. But when we, with the situation we are in the world today and with the COVID virus, it's really critical that we focus on and get more self-reliant, I think, in manufacturing our batteries for us, especially for our secure space missions.
Okay, great. Thank you. Karin, do you want to add anything?
I just echoing what both of the industry partners said. I think it was brought up earlier too, and not just the EEE parts aspect and the radiation, but I think really the extreme environments that you see are very different from low Earth orbit as you go deeper into deep space, as well as on the lunar surface. In particular, I talked about the lunar night, and so it's not just the challenge of the duration, but also the extreme temperatures you see through that. So I think that's certainly a challenge as we look at the needs for future in-space power systems.
Okay, thanks. And we understand June is back. So June, sorry we lost you for a short while. But if you have any last sentence, last statement, wrap up, and then what the topic that we asked was to talk about the biggest challenge that you see in advancing in-space power systems field, including any international competition considerations. So go ahead.
So I think I can think of two different things on this. One is from a nuclear perspective, is the appropriate regulatory framework is going to be needed. And I know the country has been making changes with that, and that will actually also extend over internationally. We have a presidential memorandum on the launch of spacecraft containing space nuclear systems that was released last year, and that's helpful. And now agencies are implementing that framework, and we just need to be diligent that the agency requirements don't end up reversing that progress. The other aspect is from an agile and synergistic technology and integrating as we integrate new technologies into our systems. That way we can build confidence and the reliability we need to support missions like ARTEMIS.
Okay, thanks so much, June. Let's see, I think we'll go to one more topic and then we'll draw, we do have a couple of questions from the audience so far. And this topic is discuss what you see as an overarching trend or next step to advance the in-space power systems field. And this time I think I'll start with the NASA folks. So Karin, would you want to open it up?
Sure. I know I brought it up in my talk, and I heard it, I think, from Darvin and from Joe as well. Sort of the infusing modularity into the designs has a lot of benefits, I think, both for NASA and industry, sort of developing building blocks that are then scalable as we see the need for higher power systems or across different space markets as well. I will say too, another trend that I've seen come out more recently is standardization in terms of the power quality. I know there is for deep space and international space power interoperability standards. So when you have, you know, maybe different companies developing different vehicles that have to dock together in orbit and transfer power across that interface, this is looking to come up with a standard so that for the power delivery, the supplier and the user know what they need to do in terms of ensuring power quality at that interface. So that's another area as well that seems to be a trend.
Okay, thank you. And June?
So I agree with the modularity that folks have mentioned. Definitely higher power systems and more efficient systems I also see is being needed, not only for science, but also human exploration. I think, as I talked about also earlier, is the idea that the fission systems and I'm not sure when I broke out before, but fission systems, they have this higher order of magnitude. We really want to return astronauts for long durations to the moon and then to Mars. I think having those kinds of power systems and the breadth of the power systems from batteries to solar to fuel cells to RPS, the fission, we're going to need that whole breadth so that we could have this evolving ability to interchange to get the best architecture that we can.
Oops, I'm sorry. Thank you. Joe, would you want to add to that?
And just to pound the point home, modularity and scalability, I think, is key. You know, as we move forward with, you know, smaller spacecraft, more constellation-oriented programs, and reusability, I think we need to get away from the point designs and get to that scalable modular system. And also, I think we need to increase our time to market. You know, you need shorter delivery times for components to get to the manufacturer, you know, with the constellations and, you know, the replace and replenish needs to be in a short time. And we don't have years in order to do that. So I think modularity and scalability will support us in that way.
Okay, great. And then Darvin.
Well, I really don't have much to add after the three folks that went before me. I agree with everything that they said. I guess I would just emphasize again the drive for high power and higher efficiency. And that's just restating what's already been said, but that's what I got.
All right. Yeah, thank you. Yeah, we really did get a pretty consistent response to that. So what I'd like to do is then go on to getting a couple questions from the audience, and Jim Way, do you have the first question?
Yeah, sure. Great. Thank you, guys. So our first question is actually for Darvin. What are the cost comparisons of SOA GAN devices versus existing silicon? Does the cost comparison include any additions or savings to the thermal impacts of unit type?
Yeah, so, so the market, although the market's been around for a long time, it's still somewhat immature in its application, in electronics. My recollection is that the costs are competitive. Real struggle with gallium nitride transistor, sorry, is proving them for in-space applications. So let's say that the latest Pareto's I've seen on cost analysis, it's typically the FPGA that is the cost driver for these type of systems. I answered the question.
Unfortunately, it seems like our feed might be getting a little choppy, so bear with us, everybody. Hopefully you guys can hear me.
Yeah.
Good. So batteries become more of a commodity as opposed to a specialty item. Basically, non-aerospace driving aerospace using those developments, or is aerospace still leading the development?
Aerospace is still, I would say aerospace is still leading the development as far as the pushing the boundaries of batteries. Obviously, commercial with Tesla and their gigafactory moving to different formats and relying on foreign entities also for their materials and their products. Obviously, the EV market is a big driver, but there's different needs in the markets. The EV markets, needs a high energy. But for space missions, it's more diverse than that. It's a wider temperature range. You really need a higher energy density. You need to get the mass as small as possible, get the launch costs down. Need to be more optimized. So, from what I see in the market, in the industry today, I do believe the big R&D pushing the envelope of technology is still in the aerospace industry.
Great, thank you.
Yeah,
so I do have one more from the audience. Let's see.
Okay, sure.
And I'm not quite sure how to put this. What do you see are the trends in allowable DoD for programs, government, civil space, commercial? Basically, they're interested in how different entities view operations which might be considered higher risk.
Yeah, there's obviously, operating at a higher DoD, you get a higher energy capacity fade over life with standard technology, state of the art today. But again, with the higher energy technology that the government's looking for now on a lot of the secure space missions, they really are looking at driving the operational mission to a higher DoD level to get the battery smaller, lighter, and less expensive. I've seen that on several programs where they're really pushing the envelope. And NAVSEA Crane, the government has multiple U.S. battery manufacturers, has their cells under test. And like I said, typically 20% is a standard LEO orbit, DoD level, but even in NAVSEA Crane, they're testing the cells at 30 and really focusing on 40% DoD operation in LEO, so pushing the boundaries a little up. I know some missions are even looking at going up to 60% DoD operations. So, a lot of that is to get the risk down. A lot of it is just life testing and demonstrating that the chemistry the manufacturer can produce the cycle life that's needed and the energy is needed. Yeah, it really, the industry, at least on the military side, it really is going that way.
Okay, well, thank you. I think that's the last question from the audience. Is that right, Jim? So what we have is one more topic I'd like to introduce then, before we wrap up. And that is, I'd like to know from each panelist what your view is of the state of the workforce in this field. And we'll kind of just go in reverse order from the way we opened. So June, if you have some thoughts.
So as we heard yesterday, and a lot of us know, right? I do. The workforce is aging, and we need to really pull in new engineers and scientists and work with them so that the NASA mission and visions can be implemented when we're no longer in the workforce. And we need to plan for this, and I have personal experience in this. The RPS program has seen 2 key members retire within the last 9 months. We're a small group, right? And so that was a major hit, and we need to have all of our responsibilities such that in a situation like this, we make sure that we have diverse teams, all types of diversity, such that we're poised to successfully support our astronauts and robots to explore more and conduct more science and change the world. Otherwise, if we do not think about this, I know it's not a technology issue, but if we don't think about this, we're not going to be able to be ready to support that in the future.
Yeah, that's definitely true. Joe, do you want to comment?
Sure. Yeah. You know, we're seeing a strange workforce, at least in the aerospace business, I think. You know, there's companies like All Aerospace in Colorado. You know, they have over 2,000 job openings right now and having a hard time fill those jobs. Same Lockheed Martin, I think, has over 1,100 job openings. You know, being in our business, you know, there's a lot of new hires coming out, but it seems like it's really difficult to fill that void that's there and the need. And also, you know, I see a lot of, you know, as June said, you know, in the workforce, there's the senior folks, you know, the very experienced folks, and then there's a gap, and then you come down to more junior people, and as the more senior folks, you know, retire and stop working, I think there's going to be an impact and the performance in the industry of being able to get, you know, new products developed and products up the door.
All right, thanks, Joe. Darvin, do you want to add to that, your thoughts?
Yeah, so there's two aspects. One, well, maybe there's 3 aspects. So certainly folks are retiring, folks that are part of space shuttle programs and satellite programs that are getting up there and retiring and moving on. So struggle with that is being able to attract young engineers to this industry. And I know from personal experience talking to young engineers, co-ops, I have some relatives that are currently in engineering school. They're really interested in the whizzy technology, the self-driving cars, the SpaceX, what they view as the really cool stuff. So it's a challenge for us to attract those that type of talent, that type of young talent. And a way of combating that or addressing that, I guess is a better word, is getting the engineers into our industry as co-ops, getting engineers into our industry as co-ops or as interns, and basically demonstrating to them that our industry is doing really cool stuff, and maturing that talent. So there's a gap between the old guys and the young guys, and we need to work on the young guys. Not much we can do with the old guys.
Yeah, I fit in that category. Thanks a lot. Karin, do you want to wrap up this question? And then we might have a lightning round question.
Sure. Just echoing what everyone else said today, as well as the discussion yesterday on this. I just want to give a big ditto to everything recommended yesterday. If there's a way to go back and rewind and rewatch that, there's a lot of good advice. To try to hit on a couple new things, I think it's important with those entering the workforce today. I know in the past people kind of picked a specialty or discipline or focus area and really had a lot of technical depth in that area. But today, I think as things change and new technologies come on the scene, the ability to learn quickly and sort of adapt. I know in my career with NASA, I've worked on a range of power system projects, from energy storage and solar electric propulsion to now distribution and control. And you know, it's good to have some level of depth for sure, but also being flexible and adapting to learning new things, I think is key. And I also think with this panel being part government and part industry, collaborating together and sort of pulling our resources and working to advance technologies is important. I do want to plug, as part of STMD, they're working with Applied Physics Lab on a Lunar Surface Innovation Consortium. And you can Google that. It's free to sign up and join. There is a specific focus group on sustainable power, and I know they meet monthly on Thursdays, with the next meeting actually being a week from today. So I definitely encourage anyone interested to sign up and join that group so we can all work together and solve the challenging problems associated with sustainable power.
All right, thanks, Karin. I do want to try for a lightning round question, so I'll ask this. We'll go in the order that we started this session with, and just no more than one sentence. Karin, what do you think is keeping you up at night? And caffeine doesn't count.
Am I allowed to answer my two toddlers?
All right. That's okay.
Probably on AMPS, we're working closely with Gateway. So how we're going to integrate some of the autonomy work we're doing and incorporate it into the Gateway is sort of the challenge I'm faced with right now.
All right, great. Darvin?
Competition from organizations like SpaceX.
Yeah.
It's that simple.
Joe? Yeah.
Yeah, the actions of some of our rogue nations, China shooting down satellites, space resiliency, and keeping it secure, I think is key.
Great. June?
The long duration of our development timelines and the costs associated with our development timelines.
All right, great. Well, with that, we'll wrap up. I think this was a fantastic panel. I can't thank each of you enough for your insights and perspectives, and extremely well-rounded panel. And I'll say this, I really enjoyed Joe's answers to the question on the commodity question, because I've been wondering that myself. So thank you all.